Hello and welcome to our convocation event on the physics of Portal 2, presented by the Society of Physics Students at Belmont University. We're going to start with a quick intro of the Portal video game so that those of you who haven't already played it can get a sense of what it's about. Just as a matter of curiosity, how many people here have not played Portal or Portal 2? Okay. 3 or 4 people. All right, excellent. Let's go ahead and roll that video.
Welcome to the Aperture Science Enrichment Center. Let's look at some of the challenges you'll face as a test participant. You may be required to perform simple tasks, such as locating an exit. These simple tasks may be supplemented with insurmountable obstacles. Thanks to the Aperture Science handheld portal device, the impossible is easy. Let's look at a real-world example. Certain objects may be vital to your success. If at first you don't succeed, you fail, and the test will be terminated. When so, remember our motto: there's a hole in the sky through which things can fly. At the Enrichment Center, we believe that a highly motivated test subject can carry out rather complex tasks while enduring the most intense pain. So in case you don't make it through the testing, goodbye. This next test is impossible. Now you're thinking with portals.
Okay. So now we're going to move into this section of the presentation. We'll talk about the principles of physics, some of them, and how they apply in the Portal universe. I'll be starting out with conservation of kinetic and potential energy. Conservation of energy in general in our universe is something that essentially there is a set amount of energy in the universe, and it's neither created nor destroyed. It only changes forms. So in this example, I'll be talking about, like I said, the two fundamentals, kinetic and potential. Potential, or kinetic energy, Ke up there, is the energy of motion. It has to do with m, which is mass, or how much stuff there is to something, and v, velocity, how fast it's going. And so the energy of something in motion is based on this equation in many cases. Then we have potential energy, which is, like it sounds, the potential for something to have some energy. So a good example, it's based on, once again, how much of something there is, and in this case, how high it is off the ground. So a good example of how something would have potential to have an energy is if, say, someone's standing on a ledge, and that ledge, their ledge is a certain height off the ground, and if they were to jump off it, they would then start gaining a certain amount of kinetic energy from their fall and the motion of their fall. So potential energy represents that potential to have a kinetic energy. So, got a video for it? Okay. So, as you saw from this video, once again, we stood up on a ledge, had a certain amount of potential energy, then we jumped off that ledge. Our potential energy started getting converted into kinetic energy. The closer we got to the ground, the less potential energy had, the more kinetic energy we had because the faster we were moving. Then we went through the portal, and as soon as we came out the other side, the other portal, all the kinetic energy started going back into potential energy the higher we rose. So the fact that we rose back to the same height as the ledge we were on before we jumped, after we went through the portal, means that energy was conserved through the portals. It all just went from potential to kinetic and back to potential.
Hey guys, I'm Sarah, and I'm here to explain to you about momentum and how portals do or don't affect momentum. So momentum, you can think of it, well, mathematically as mass times velocity, so you'll have to think of it that way. But what that means is that the more mass an object has, or the faster it's going, the more momentum it'll have, and vice versa. Also, just as a note, it's a vector, so it means that it has a magnitude and a velocity. So if an object has an amount of momentum and it's going that way, it's different if it's going that way, so direction matters. And there's a couple ways you can think about momentum. You can think about it in relation to inertia, in that the more momentum something has, the harder it is to change it. So if, say, a mouse was coming at me, I could just bat it off like easily because it doesn't have a lot of mass. But if it was a semi, I'm getting out of the way because there's no way I'll affect that really. And the same goes, if someone like propelled a mouse at me like going at 50 miles an hour, I'm getting out because it's going so fast, its momentum is so huge, I can't stop it. You can also think of it in terms of Newton's first law, in that if an object has a certain momentum, it'll keep that momentum until an external force changes it. So if that mouse was in space, going like this way, floating off, it's gonna keep floating off in that direction and in that velocity until something changes it. And I guess we can move on to the video. So just in case that video wasn't clear, I made a little picture. So what we were trying to do, we were here up on this ledge and we were trying to get over here onto the second ledge. So what we did was we made a portal up here so that we'll exit out of. And then we fell down this ledge, made a portal down here, fell into it, came out of it, and landed on this ledge, a happy man. And the only reason that's possible is because when we go into that portal, nothing changes about our speed. Like the speed that we enter the portal is going to be the same speed that we exit the portal. So if that wasn't true, what would happen is we fall down here and then we just plop right back here onto the ledge. Or maybe we'll go flying, but it doesn't change our velocity. But does that mean that our momentum is conserved? Well, there's two ways that you can look at it. You can look at it in the point of view of an outsider, as in this picture. When we enter the portal, our momentum is in this direction, going down. And when we exit the portal, our momentum is going out in that direction. And since momentum is a vector and its direction's changed, that means that its momentum has changed. But we can also look at it in terms of ourselves when we play it. When we play it, we look at it in the point of view of the player, the character in the game. And for them, it doesn't change. Can you move on to the next slide with the two figures? See, when in relation to the portal, our momentum doesn't change. See how our momentum is going that way? It's perpendicular to the portal. And when we come out, it's still perpendicular to the portal. So in the point of view of the player, it doesn't change. So the magnitude of the momentum is conserved always, but the direction is only the same in our point of view of the player. And that's all.
All right, Stuart, can you go ahead? All right. Actually, go back 2 slides real quick. I just want to point something out Go back one more. So you'll recall Toast giving his talk about conservation of energy. One thing I just want to point out with the portal universe is that kinetic energy is conserved by a portal, but potential energy is not. You'll notice that when we start up here, we have, say, all potential energy, no kinetic energy. And then by means of the portal device, we're actually coming out up here. So we have more potential energy, and we've also got kinetic energy from down here. And so that's a violation of global energy conservation. But as we pointed out locally, in a nearby neighborhood going through the portal, the kinetic energy is still conserved. So that's kind of a funny thing that happens. And if you were able to make portals, you could actually exploit this to generate infinite amounts of energy if you wanted to and have a perpetual motion machine. We generally don't allow for that kind of thing in normal physics, but we'll talk about that some more later. Go on 2 slides forward. All right, so I'm just going to talk briefly about projectile motion. And so when we're coming out of that portal, we've actually got no forces in the horizontal direction. So our position in the horizontal direction, x, is just linearly proportional to the time, t. Whereas in the y direction, in the vertical direction, we've got whatever our initial y velocity was times time, but we've also got this acceleration due to gravity, and that goes like 1/2 times gravity times t squared, and the g there stands for 9.8 meters per second. Well, we can take our t here and just substitute it in there, and so we get an equation for y as a function of x. We'll notice that it goes as the second power of x. That's the equation of a parabola. And so the paths that we take through space as we're flying through the air is going to be parabolic. And we just thought we'd point that out in case some of you haven't had physics yet. You can learn more about these sorts of things if you take a little bit of physics here at Belmont University. And with that, we're going to go on to the next slide. Oh, we have a video. Would you like to see the video? Yeah. All right, let's do it.
Spectacular.
Isn't that great?
Hey everyone, I'm Austin. I'm going to talk a little bit about oscillatory motion, and I have a big old spring-loaded system, and we're going to... all right, so in our universe, we have a thing called Hooke's law and linear restoring force, and it's simple harmonic motion is what Hooke's law is describing. So this spring, we can kind of show you what's going on. So right here we have a equilibrium position. I'm not applying any force to it. It's just sitting here, and this is where it's going to rest. But if I apply a force to it, this the distance I go from the equilibrium position is just x. K in this equation you see right here is the springiness of the spring, or how much the system wants to be back to equilibrium. So I'm going to apply this force x to this system. I'm going to apply a distance x, and this force, now you see there's some sort of force because it's going back and forth. Well, this negative sign here is this linear part of this linear restoring force. It's going back, it's pulling it back towards the equilibrium position. So I go down, the negative sign pulls it back up. If I go up, the negative sign is telling you that the force is going back down. And something that you can get from this pretty quickly is that amplitude and frequency are independent. So because as you go further away from the equilibrium position, the force is becoming larger, it means that if you go very, very far away, you're going to be coming back towards the equilibrium position very quickly. And vice versa, if you go just a short distance away, you're going to be going a little bit slower. So an example of this would be like a guitar string. So if you pluck an E on a guitar string, it's going to have a frequency of E. But if you hit it softly, it'll be an E. If you hit it very hard, it's still going to be an E. So the frequency is going to be the same no matter how hard you hit this thing. But the thing that's changing is the amplitude, how far it's oscillating away from the equilibrium position. Well, we can let's go to the next. Yeah. So in Portal, you guys saw the video right at the beginning. We had things going in and out of portals, going back and forth. Well, there's an interesting thing about this is that it's not simple harmonic motion, which is not something that really happens in our universe. I mean, things like molecules vibrating are going to be simple harmonic, and sound going from me to you guys' ears, that's simple harmonic motion getting to you. But in the Portal universe, you can actually make this motion with a constant restoring force. So as it's going in and out of the portal, gravity is just pulling it straight down. And as it gets higher, gravity is going to be the same. I mean, gravity's not going to get greater. It's not going to become greater as you get further away from the portal. So you just have this restoring force that stays the same the whole time. And that means that the further you get away from the portals, that frequency is actually going to be smaller. It'll take a longer time, so the period is getting larger and the frequency is getting smaller. So let's look at these videos and we can see an example of this. All right, so the first one is this short fall. We can see that we have a pretty short amplitude, and it takes a pretty quick, I mean, it's just a quick right back and forth. And this next video we have, it'll actually be a longer fall, and you see that the period is longer. So this is something that you really can't do in our universe, but you could do if you had some portals. So that's kind of interesting.
So now that we've talked about the basic physics of Portal, we're going to introduce some of the interesting features that Portal has, and I'm going to start with the long fall boots. Now, Shell can fall a really long way and not die. That's kind of different from our universe. So I'm just going to let y'all see an example of this in this video.
Hello, investors. Kenny Johnson here. Now, I know you sunk a lot of money into the dual portal device, but I'm here to tell you we're not banging rocks together over here. We know how to make a quantum space hole. Harold, see? Portal here, portal there. Look at this thing go. Now, we have run into a reproducible human error problem. A lot of expensive equipment getting broken. But don't worry, Dave took care of it. I give you the long fall boot. Think of it as a foot-based suit of armor for the portal device. I'm not going to lie to you, it's expensive as hell. But check this out. We told this test subject to just go ahead and try to land on her head. She can't do it. Good work, Boots. So anyway, we're going to be back right now. Just make those checks out of cash. Okay, Johnson, we're done here.
Okay, so the terminal velocity of a human is about 2,007 meters per second. And so we can calculate the momentum by multiplying by the mass. Momentum is mass times velocity. So we come up with this very large force. And then we know by the impulse momentum theorem that the change in momentum equals the average force times the change in time. So we can find the average force by dividing our change in momentum over our change in time. And so we get this force, and that turns out to be about 200 Gs. That's a really large force. The most number of Gs ever survived by a human is like 100, and that was in a NASCAR race or something like that. So it's pretty unlikely that she could actually survive this fall. And we were pretty generous here with the change in time, too, because the actual impact is not as long as 1 second. It's much shorter, and so we would end up with a much higher average force. So y'all can think about that as you watch this next video and see how she would die.
Hi, I'm going to talk to you about Propulsion Gel. Propulsion Gel is this orange gel that is introduced to you in the game. The game makers claim it's made of fiberglass, and essentially what happens is whenever you move on this orange gel, it increases the velocity in whichever direction you're moving. A real-world example of something like this would be the moving sidewalks in large airports. Where you can walk at your normal speed, but you're passing people who are also walking. Except that's moving in one direction. And this gel, you stand on it, no matter which direction you move, it's going to accelerate your velocity. This would require some sort of added energy. Fiberglass wouldn't do this. And I don't know of any other material that would not violate physics. So let's watch this video. So as you can see, a short, maybe 30-yard run on this orange goo was enough to propel you straight across that chasm without jumping or anything. There's no material that we know of that would do this, but that's propulsion gel, and it's pretty useful in the game for solving a lot of puzzles. You couldn't really do it without it. So.
Okay, so I'm going to be talking to you about bouncy gel, or the game calls it repulsion gel. But so this is kind of building off the energy concepts I told you about earlier. And what bouncy gel does for you is it augments what would usually happen in a collision. If you think about a collision, may not initially come to mind, but think of a car crash, a head-on collision between two cars. When they smack into each other, each car had a certain amount of kinetic energy based on their velocity. So when they smack into each other, all that kinetic energy is given off in the form of heat, sound, all sorts of things, and they essentially come to a stop. With what the bouncy gel can allow you to do is not lose that kinetic energy when you run into something that's coated with the bouncy gel. It conserves the kinetic energy and just makes you come right off with the same speed that you ran into it in. So. A little laggy, but you get the point. It was a fairly large fall, and almost like a trampoline, bounced him right back up to the same height he had been. So this stuff is really useful in the game, of course, for solving puzzles, but one thing I wanted to also mention is this coefficient called the coefficient of restitution. I like to refer to it as the coefficient of bounciness. It is how bouncy something is. And this coefficient ranges from a 0 to a 1 in value. And what this basically represents is, like I said, how bouncy it is. So a pool ball, if you think about a pool ball, collisions between pool balls, they bounce off each other pretty well. And it's got a coefficient of about 0.95. This gel, we suspect, has something a little higher than 1, something that, is impossible in normal physics, but it actually adds energy to you in some cases. So there you go.
Hi, everyone. I'm Ben. Can we play the video first?
These bridges are made from natural light that I emitted from the surface. If you rubbed your cheek on one, it would be like standing outside with the sun shining on your face. It would also set your hair on fire. You don't have to redo it.
Yeah, so light bridges, it's kind of a tricky thing. You look at that and you say, okay, yeah, right. Well, light actually does have momentum, even though it doesn't have mass. We've been talking about momentum as mass times velocity. But light has momentum. And you also get this idea of radiation flux, or radiation pressure, which is basically just the force per unit area going through a surface. Now, you've probably never experienced radiation pressure because it's minuscule compared to something else called the Poynting vector, which points in the direction the light's going. We get a nice pun from that, so that's good. The Poynting vector is the power flux density, which, that's a mouthful. Basically, if you just look at how much Poynting vectors going through a surface, you get the power that may or may not be absorbed by that surface. Now, if you're talking about like a rubber boot, that absorbs most of the light energy because it's black and, yeah. Now, thinking about radiation pressure, if we felt radiation pressure on an everyday basis, when you turned your car into the sun, it would be like you got extra drag, but you don't feel that. However, if you leave your car out on a hot day and touch the hood, it's really hot. And so I decided to ask the question, what if your rubber shoes absorbed all the energy that for a system with enough radiation pressure to keep you up? So next slide. Basically, the Poynting vector and radiation pressure are related by a factor of c, and what I found is that if you had enough radiation pressure to keep you off the ground, your shoes would light on fire in about 3 milliseconds. So that's why you don't experience radiation pressure ever. Now, that's not to say if you had perfectly reflective shoes, you could almost skate across and you actually wouldn't absorb any energy. So that's possible. However, if you look at the video, the light's actually kind of pointed in the wrong direction. It'd have to point up. And so if your shoes are absorbing it, your face is probably absorbing it too. And as Gladys says, you might not want to rub your cheek against it.
All right. By the way, I'm Dr. Hawley. I'm the chapter advisor for the Society of Physics Students. And usually every semester we try and work together some sort of convo event. In the past we've done sort of Mythbusters treatments of various stunts in movies, like we did physics of Iron Man and Batman, The Dark Knight. But this time around we thought it would be great to take on a physics-based puzzle sort of video game like Portal. Well, one of the things that Portal relies on is this notion of connecting two different places in space, two different places in the universe. And so the word that's been used for these sorts of topological defects is called a wormhole. So wormhole is an idea of a feature that connects two different places in the universe, two different locales. And the mathematics of connectedness is called topology. So that's why we call it a topological feature, a topological defect. Next slide, please. Well, the first wormhole solution that ever appeared was actually in the first black hole solution. Back in the around 1915, Carl Schwarzschild, supposedly on the back of his rifle in World War I, was working out the first spherically symmetric solution to Einstein's theory of general relativity. And so you can get a black hole solution, and this is a sort of a schematic diagram of a black hole. We've got these different regions of space-time. We've got time going this way and space going this way. This is our universe, this sort of diamond-shaped thing over here. And this over here, this line, that's the black hole horizon, the event horizon. And up here is the singularity. You'll notice if you're in this universe and you cross the black hole horizon, pretty soon you hit the singularity, and that's where you die. Well, right here on the other side, there's actually a totally another universe. And these lines are actually going at the speed of light. So you can't actually get from this universe over into that universe. But right here at this time, there is actually a spatial feature that looks like this. And this is a wormhole. It's not a traversable wormhole. You can't go across it because this only exists for one instant of time. All right, next slide, please. Well, there's another black hole solution where if you give the black hole charge and you make it spin super fast so that the equator is spinning at the speed of light, then you could say be in this universe, and the picture of the overall space-time is completely different. In this case, the singularity is up and down. We say it's time-like. You can cross the black hole horizon and then come out of what would be a white hole in another universe. You come out of here, and so you can actually traverse through here and come out in another universe. And this is going through the black hole and coming out in another place. And this is what science fiction stories are made of, right? Now, astrophysically, we would not tend to see black holes with enough charge to do this, because if there's a large amount of, say, positive or negative charge, it's going to tend to attract the opposite charge around it from whatever gas particles might be nearby, and render itself electrically neutral. So we don't tend to see the Reisner-Nordstrom black hole astrophysically. If we go to the next slide, what we get if we collapse a star, we don't actually get any wormholes. The collapsing matter actually ruins all this otherwise interesting stuff off to the left and up to the top here. And so in our universe, real black holes, astrophysical black holes, don't have this feature. So, how do we come up with wormholes? Well, next slide. Well, it's been postulated that perhaps on very, very small spatial scales, on the so-called Planck scale, that a quantum theory of gravity would render a space-time which is sort of bubbling all the time. It's like a foam, and we have all these tiny little connected wormholes. They're very, very tiny, and they only last for a very brief period of time. But the thought is, what if you could grab one of these things and then somehow stretch it out and then somehow make it stable so that it doesn't collapse again when you want to use it? So let's go to the next slide. So if you manage to generate such a wormhole, it would tend to close up on its own as soon as you try to put some kind of mass or matter or energy through it. And in order to counteract that, you'd need to find some kind of matter with a negative energy density, which doesn't really make a whole lot of sense. Again, it's one of these things where if you had some matter with a negative energy density, you could become the richest person in the world because it essentially gives you something for nothing. That is a problem, but despite that, there's a lot of interesting things about gravity that people can learn by studying wormholes. And just as a note, just to show that some people are taking this very seriously, let's go to the next slide. Well, I guess a few months ago now, there's a paper on the General Relativity and Quantum Cosmology archive server from Igor Novikov, who's quite a big name in general relativity theory, about a new model of a wormhole. Also, Kip Thorne, who's at Caltech, has done a lot of work on wormholes and the like. And actually, if you're interested in learning more about this, he had a bestseller that was written for lay audiences called Black Holes and Time Warps. And it's a great book. It's got lots of pictures. It's got very little math. It's got a lot about the story of physics in the 20th century, a lot of biographical information. It's a good read, so I would recommend that. And let's see what's on the next slide. All right. Well, let's have all of our students come on up for our Society of Physics students. By the way, this is Stuart. He's our president, and he made a lot of this happen. We want to thank Leslie Redd and the rest of Valve Software. Come on, everybody. Let's get in front of here. We don't have any cake for you, but of course that's the joke, right? Belmont University for, well, sponsoring us as a society, and Aperture Laboratories, which is a fictitious company, but we got these sweet shirts. So we're going to take some questions, and once again, to anybody out there watching us in TV land, come to Belmont, major in physics. All right. What we're going to do is, if you have a particular question, maybe you could even direct it at the person that seemed to give that talk, and if you don't know the names, that's okay. We'll help you out. Do we have questions?
Hello. In theory, if you were to try to make a perpetual motion machine, how would you attempt that? Like, say that the circumstances were perfect to set up something like that. What guidelines would you follow, or what would you follow to try to make that?
Let me take it. Well, in the portal universe, you could just create a portal in the floor and a portal in the ceiling and step through, and you'll just keep falling forever. And if you wanted to harvest that energy, well, just use a slightly larger room. And so as you're going down, maybe you hit some kind of plate on your way down, or you rub something, some kind of friction that'll take away some energy from your motion. And then when you hit the portal and you come back up, you've got all that potential energy back again. So that would be one way to do it.
Or going off that same idea, a practical way would be, as you saw the gels easily were transported through the portals, conserving energy. A water turbine, just like an old water wheel, would do the same. Yeah. As the water falls through, turns the turbine, you wouldn't run out of energy.
I think you can actually see one like Dr. Hawley's talking about in the intro video when she's kind of... So, there you go.
Any other questions?
If this game were possible, would you have to consider like different the reactions between different things going through the portals, or does it not matter? Like putting those bouncy gels, or putting different like, would it react differently within the portal because it was a different substance? Or
I think the whole point of the portals was that like everything in our universe is essentially conserved through them, other than the fact that your position of the portals can violate a few things. But things traveling through the portals still act in the same way as they do in our universe. So if it had a reaction out just in regular space, if it was in the portal, it would have the same reaction, or at least should.
Also, the volume of the portal is very small. You can't like climb into one and like lay down your sleeping bag and take a nap and then climb out the other side. As you pass through one side, you come out the other.
Okay, well, we want to thank you for showing up. Let's give these guys a hand. All right, and Alicia here is going to have our Convo scanner, and she'll stand right by the door, and you can come by and give her your card. Any other questions you have, direct it to our people here, and thanks for reviewing.